Okay, made it in time. Then okay. Good. Let's start. The group gets smaller and smaller, but maybe live stream people join at some point. Ah, phone forgot. If half the audience is online, I should probably check for person. Okay. Last time we spent an hour or so on proving these tail inequalities or concentration bounds, basically 3 different types. We started with Markov's inequality. That one. Basically, you just need the expectation, and then you can relate x to being much larger than that expectation. But that turned out to be too weak. If you apply that inequality to some more extreme variable, then you get Chebyshev's inequality, which already is enough to prove some asymptotic convergence for random variables, but the convergence speed is not strong enough for what we normally need. And so the final thing that we ended up with for a more specific distribution here, really that I wanted to copy this part, specifically for the binomial distribution, we can make this very strong statement from the Chernoff bound. The deviation, even just a tiny bit away from the expectation, is exponentially unlikely. Where a tiny bit has to be, taken with a little bit of detail. You have to pick delta so that it is big enough to counter. And now we want it to be small. So delta has to be small. You can't make it so small that it cancels the n. That's the way to put it. You want something of the negative growth of this exponent to be left over after you inserted delta, which is something that shrinks with n. And the product of this still has to be a growing thing. We'll see that in the applications. So started this briefly last time, but let's forget about it and pretend we haven't seen it. In the next section, we'll finally apply the concentration bounds, mostly the Chernoff bound, to some concrete algorithms, both to show you that it's useful and to see how they are used. I might try to go a little quicker over this. There's past recordings where this is done in maybe more excessive detail. The first application is our standard strategy to boost the success probability for Monte Carlo algorithms. Said already, if you're not happy with an algorithm that's wrong half the time, you just repeat it several times and take whatever the majority vote gave you. And we can even be more cautious. If there is no clear majority, we say we failed. So here is that formally written up. You do t independent runs of your Monte Carlo algorithm on the same input x, but with fresh independent random bits. If at least t have rounded up, many runs yield the same result, then we output that. I guess we always pick an odd t, so just that there's no ties. And otherwise, we give up. So how good is this? And it turns out that depends on the exact type of the Monte Carlo algorithm we have. Here we look at bounded error Monte Carlo. So in particular, if you remember the definition, this meant that the probability that this algorithm A on an input X is the correct output, this has to be at least 1/2 plus some epsilon. And this epsilon must be independent of the input that we pick. There's an absolute constant depending only on the algorithm so that we can bound the success probability away from 1/2. That was bounded error. And now we're saying if we have such an algorithm, whatever the exact epsilon for this algorithm is, we can make it with high probability. So essentially make epsilon subpolynomial, shrinking like 1 over a super polynomial function. Little o of n to the minus c for all constant c. By just a moderate number of repetitions, slightly more than logarithmic. So let's see how to prove that. The goal will eventually be to use the Chernoff bound. So let's keep that handy. Might have to make this a little smaller in the end. We'll see. So the goal is to do something where you can apply the binomial Chernoff bound. So we need to somehow generate a binomial distribution. For all intents and purposes, you can assume that t is log squared. This is just for you to keep in mind. It would actually be good enough to take log n times log n or whatever else small growth above log n. But that's kind of morally the idea that you should keep in mind. So we do t repetitions. That means we can define t random variables, x1, x2 up to xt, where xi is the event with a random variable that the ith run succeeds, which means produces the right output. Right, so on our input x, we actually get what the function is supposed to output. And so this is an indicator random variable of this event that the ith run satisfies this. And of course, this is a 0, 1 variable. So it has some probability to occur. And we actually know a bound for this probability. Now, because we pick the same x, we don't know exactly what p is, but we pick the same x and we do independent repetitions. So really these, the sequence is IID, independent and identically distributed. And it has some Bernoulli p probability or Bernoulli p distribution for each xi. We just don't know the p exactly. We know a lower bound. But we can pretend that it is known exactly. Then the algorithm will only be more likely to succeed. That makes the calculations a little easier if you don't have to have another inequality flying around. So we'll assume that we have exactly 1/2 plus epsilon for some constant epsilon greater 0. Now, if you define x by summing up all those indicator random variables, we get something that's a binomial distribution by definition. T repetitions, each event occurs with probability p. So what's the sense of doing that? Well, we can now express that our overall algorithm succeeds, or rather that it fails, say. The majority vote fails if and only if we have not enough summands summing to 1. So if and only if x is too small. Yeah. Let's always assume that t is an odd number just to avoid kind of stupid corner cases. I don't think that adds any interesting twists to it. Okay, now we're essentially in business. We have reformulated our algorithmic problem as a purely statistical one. What's the probability that a certain binomial is at most that value? And so let's calculate the probability for that to happen. The probability that x is less than, let's be very strict, so oh, come on. I'm making the event less likely. That makes the more likely. I'm making the condition weaker by dropping the floors. So that is a more likely event, which means the probability can only go up. And now we have to rewrite that in a form that matches the Chernoff bound. Maybe we can afford that on this page a bit bigger. The point is we need to rewrite it so that it matches that form. So we have to subtract the expected value and it turns out it's more convenient to flip it around and add p on both sides. So we do a whole rearrangement. Okay, let me first write it down. So what have we done? I added p on both sides. Well, we divided by t first, then we have x divided t less or equal 1/2. Then multiply that by -1, then you have minus x over t greater or equal -1/2, and then we add p. So that's the same inequality, just rewritten. And so that's close to what we need. This is the wrong way around, but we'll take absolute values. But this expresses that essentially our random variable is much smaller than the average. That's half of the tails that we bound with the Chernoff bound. So we make the event again more likely by including both options being way too small or way too big. And so formally we express that as the absolute value to be greater than what we have, p minus 1/2. And so that's now in the form that we need for Chernoff's bound. In particular, this p minus 1/2 is exactly our epsilon, which is greater than 0, so that matches. It's called delta in the bound, but it's other than that the same. So here we applied Chernoff bound. And we have to insert what we have on the other side. So it's 2e to the minus. Then we have delta squared, which is epsilon squared in our case. And the n is a t because our binomial has t repetitions. Okay. So far, so good. That's the probability that t repetitions fail. Now, we're claiming that this is not happening with high probability. This isn't happening. And so if you remember what that means, for every exponent c, we have to show that the probability is in this little o of n to the minus c. So we're given such a c, and we compute n to the c times the probability that this algorithm fails. If that goes to 0, then we've proven the little o of bound. majority vote fails. So we claim that this goes to 0. And from this, we would follow that the probability that this fails is in little o of n to the minus c. Because c was arbitrary, that implies that the algorithm doesn't fail. With high probability. Now we still have to show that this convergence here is true, but that's not actually that hard. Using our bound from above, we can, let me copy it once. So we take this, we use our bound from above, this one. And I'm going to put the n to the c into the exponent. So everything is within an exp. And then I have c times natural log of n. And we have the minus 2 epsilon squared t. And at this point, we have to use what we know about t, namely that it is a super polynomial. Which means we have some constant times log n minus another constant times something that grows much stronger than log n. So that means the overall thing in the exponent goes to minus infinity because the second part dominates. The t grows bigger. So the exponent goes to minus infinity, which means the exponential is going to 0. And that's what we claimed. So this is prototypical of the type of with high probability proofs. We apply Chernoff bound. The creativity goes into how to define the xi. Here it was very simple because we just repeat the same thing several times. Then we reformulate what fails means in terms of bounding a binomial. And again, the magic is majority means exactly t half is our threshold, but the success probability is slightly bigger than 1/2. So there will be, when n gets bigger and bigger, there will be a linear difference between t half and the expectation t times p. And that's what we use here. So in this case, you get this exponential upper bound. Then the second step is also always the same. If you show with high probability, you have this n to the c factor that you're supposed to dominate. Well, the probability is supposed to go to 0 faster than this n to the minus c. And so you multiply this together, put it in the exponent, and make sure that the exponent goes to negative infinity. Okay. This was nice. To finish off this part about majority voting, let's drive home the point that really unbounded error is pretty much different. So the formal statement here says, okay, you can still do majority vote, of course, but there is an example where you have an unbounded error Monte Carlo algorithm that even has a restriction. It uses a linear number of bits. It could use polynomially many, but here, say, it only uses a linear number. And then we can say, we can guarantee that the majority votes, even to reach a certain fixed probability, we don't even aim for high probability bound, requires already super polynomially many repetitions. So there's no way to turn an unbounded error Monte Carlo algorithm into a bounded error Monte Carlo algorithm while keeping the running time polynomial. We're basically just showing here that the trivial way to do it fails. It's it's not actually supporting my statement, but we'll come back to that in the next unit. We start with essentially the same kind of setup. So all we know is that the success probability now is strictly greater than 1/2, no bound. And for sake of the argument, again, I guess we can say that the number of random bits is exactly n. You'll see this doesn't really change anything. But at least in the worst case, A now has a different run for every random input. So here it would be 2 to the n different runs for the same input, depending on the random bits. And of course, these are equally likely the way we define things. So each has probability of being chosen 2 to the minus n. Okay. That means we can follow the same approach as above. To get that the majority vote fails if a random variable x is less or equal to half t half. And again, x is a binomial distribution, but this time all we can say is that the probability here, p, is strictly greater than 1/2. But we can say a little bit more under this assumption, because remember, the probabilistic Turing machine, everything is deterministic once the random bits are chosen. And if I only have 2 to the n different runs, and it has to be strictly greater than 1/2, we actually know it could be 1/2 to the plus 2 to the minus n in the worst case. Like it has to be at least that big. And let's suppose that we pick an algorithm where this is indeed the worst case that happens. So in reality, the bound on the probability is not completely unknown, because the number of different runs is not completely unknown and unbounded. It depends on the number of random bits that you use. You can still make some statement about the probability. But the key thing here is that this epsilon is going to 0 and even exponentially small. So we maybe smell the trouble there. Okay. Now the rest is a bit of rote calculation. There's one step which may be worth doing. So maybe let me try to give the argument. First of all, we show that now if we take our x and we try to get into the range t half and the expected value of x, this is actually very unlikely. That's again gonna use Chernoff bounds. So what does that mean? If the number of equal outcomes is a majority, but below the expected value, we shouldn't expect it to be much larger than the expected value. So this is the range where the majority vote succeeds, right? But unfortunately, this is this needs this is actually not yeah, you want this probability to not be so I guess it's one part of where we have success if x is larger than the expected value. will also succeed. But this range is not very likely. Because the binomial distribution is symmetric. The probability to fall above the expected value is exactly 1/2. We only need an upper bound. So from these two things, the probability that the majority vote overall fails is again the probability that our x is too small, less than t². And that is at least as much as the probability that t is strictly less than t², okay? And we'll use that to rewrite for the two parts. So there's if you think about the whole range that x could take, there's t² here in the middle. And then the expected value is slightly bigger. It's a tiny bit to the right. The range where we succeed is this green part. Sorry, x is greater than t². That's the green. That's where our majority vote is happy and succeeds. And so the probability that it fails is the converse probability, and we express that by taking the probability to be below the expected value and subtract the probability for the part in between. Yep. So that's this tiny bit here is that blue part. And so we know this is at least 1/2. It's essentially 1/2. So this should be greater or equal. And if the random variable is symmetric, you have exactly the same mass left and right of the expected value, but because it's discrete, the expected value itself could have non-zero probability. So it's 1/2 plus the probability to hit exactly E of x. But what we need is an upper bound here, so that's right. And what we subtract is an upper bound on this thing, so what we subtract then turns into a lower bound. So we have this epsilon t 3 to the epsilon t. And we'll see that this essentially converges to 1/2. So it's not going to be that's what we want to show. If it was to converge to something, well, that's the probability that it fails. And if we can show that this converges to 1/2 unless you pick an absurd large t. So suppose we pick a polynomial number of repetitions. And recall the epsilon was this 1/2 to the minus n. Then what do we get? 2 to the minus n, n to the c, 3 to the 2 to the minus n, n to the c. So essentially this part is going, that the exponent is going to 0 very quickly. So the exponent part is going to 1. This n to the c is fighting against an exponential, so the exponential wins and the whole thing goes to 0. So what does that mean? If we do any polynomial number of repetitions, the majority vote fails with the probability that converges to 1/2. In particular, it is below any kind of delta or any delta greater 1/2 for sufficiently large n. And so no polynomial number of repetitions suffices, right? Okay, what we still have to show is this claim up here. I should say we will show. And so that's this blue bit. Probability that x lies in the range between t½ and its expected value less or equal epsilon t3 to the epsilon t, right? Yep. This is not something where you can use Chernoff bounds. So there, the easiest argument I found was essentially going by the definition. So we take this, take this guy, just plug in what we know about that. It's a binomial distribution, so we know what the probability weights are like. And okay, let me try to write this a bit cleanly. The values for x range from the lower bound, so t½ excluded, so let's say t½ plus 1, up to the expected value is p times t. But we know what p is. That's ½ plus epsilon. So we have t½ plus epsilon t here. There's a plus-minus rounding issue here that I'm trying to sweep under the rug to not make the calculation uglier than needed. And what's the probability for a binomial to have a certain value I? It's the binomial coefficient, and then this I times the success probability, and the counter probability for the other attempts. All right, so that's just the probability that binomial, again, remember x is a binomial with parameters t and p. And so that's just the probability that x has this value t, I, sorry. And so we're going to bound this a bit. And it turns out you can be relatively generous in how you bound it and still get this upper bound. What's this pen doing? So first, let's leave the sum aside. The binomial coefficient So this whole probability has a certain shape. It goes up and then goes down again. So it has a peak at the expected value. If you plot that as a function, this gray thing. And so we can upper bound the sum by replacing all summands by the largest summand. Okay. And so we'll do, I think one step further would make sense here. We're summing from t half to something larger, so the largest is actually the first summand. But, just plug that in. Then we have 1/2 plus epsilon to the t half, 1/2 minus epsilon to the t half. So largest summand. And you can upper bound this binomial coefficient. If you think about it, so it's a set of, we're picking from t elements, t half elements. That's effectively, it's effectively like a bit vector of size t, where you know half of the bits are 1. But certainly this binomial is upper bounded by 2 to the t. So let's just use that here, that this is at most 2 to the t. That's a generous upper bound actually, but doesn't hurt. And if we want, we can write that as 4 to the t half. Turns out that's convenient, so we can now rewrite. The trick that with changing the sum is that now all summands are the same, so I just get the number of summands, which is epsilon t, times the summands themselves. And there we have 4 to the t half, and then these guys all to the t half, so it's one big exponential. Half plus epsilon, half minus epsilon, and the whole thing to the power t half. So I wonder if I was too generous at that point. Okay, let's see. So this bit in the sum here, you can multiply this out. So it's 1 minus 4 epsilon squared. And you get a quarter from the 1/2 squared, and then minus epsilon squared, and the whole thing times 4. That's certainly less than 1, so you get that here. Then I only get an epsilon times t upper bound. I had an additional factor written down, but I'm not sure where to get that from. Let's see if we need this 3 to the epsilon t here, really, because it went to 1 anyways. Might simplify the argument a bit. So I'm gonna say this is not needed. So let me remove that bit. And that wouldn't change anything. It just makes this a bit easier. Maybe it's just that I was generous here. I think I was overly cautious back then and upper bounded not the entire summand by the largest summand, but the individual parts. So this part is biggest for t half, this part is biggest for the other extreme point for I, but I don't see why we would need that. So should be fine. And so the argument is slightly shorter. Again, the point is unbounded error is not good enough. We need an exponential number of repetitions. So that's an indication that this is not a suitable model. At this point, I thought it's useful to make a short comment on what happens with randomization in optimization algorithms. Because the majority vote that we've just discussed makes a lot of sense if you have a decision problem where there's only yes or no outputs. If you have an optimization problem, you could have a randomized algorithm that outputs any kind of feasible solution, but it need not necessarily be an optimal one. Then if that's the situation, why would you follow the majority vote if you can just compare from all the solutions you got which one was best? And so a natural approach for optimization problems would be not to do the majority vote, but just output the best solution you've ever seen in all the random trials. And then this is a natural thing to do. We'll have sometimes a hard time proving that this is doing any better than the majority vote. And we'll kind of reserve this for the approximation part. So for this chapter, we only allow the exact optimal solution. And then the whole theory is essentially equivalent to requiring that you have a majority vote. This doesn't seem to make a big difference. There's more to come. I just wanted to make this point here because if you think about randomized algorithms for, say, a vertex cover, and if any of the independent runs found a smaller vertex cover, why would you go with the majority vote? And obviously, you wouldn't. This is more to make the theory around for the decision problems. I have one last example where I'll only sketch the proof, and I'll refer you to some old recordings if you want to see the full details. What we've used so far is essentially the Chernoff bound in its very raw, plain vanilla form, because the majority vote does exactly identical repetitions, and that seems like an obvious fit for the Chernoff bound, but maybe this is not always as easy. And so there's an example where you can, with a trick, apply the Chernoff bound still, even though it's not obvious why there would be an independent repetition of things. And that's this statement about quicksort. So you'll remember what I mean by randomized quicksort here is that you pick a random pivot in each step. The other thing we have to talk about is the recursion tree. What do I mean by that? The original input for quicksort is some array. And then you pick some pivot. We don't know up front where it will be, but after partitioning, I know maybe it lies here. That's my first pivot. And then I know these are lesser equal, these are greater equal than the pivot. Let's just write P. And I'm going to recurse on the two sides. And so I naturally get a tree from that, where this is the root, and then I have vertex here or node here. And there will be some other pivot in this part and maybe here as well. So I keep splitting this until the parts are tiny. And okay, if I draw this until the end, we're going to sit here for a while. So let me stop here. The thing is, on each level, if you sum up the effort on every level, you have linear costs for each of them as an upper bound. Maybe some levels are not empty, are partially empty. Let's do one more here. Because some elements already are done, and so they don't have to participate any further. It's always a most linear. So you have a linear cost on each level. If you can bound the height of this tree, you get a bound for the overall number of comparisons. That's what the corollary says. If you can bound the height of this tree, then the number of comparisons follows. And so we're interested in the worst branch of this tree. Intuitively, you can say in each step you follow the bigger subproblem. But of course, that's only an expectation true. Really what you mean is the height of this tree, the longest path from the root to any leaf. So if we show that this is logarithmic, then we have shown that quicksort has order n log n cost, not only in expectation, but with high probability in our strong sense. That's the reason why you'll essentially never see quicksort fail in never go quadratic if it's properly randomized. Maybe let me be picky here because the statement kind of hinges on the fact that you don't have duplicate keys, because then the randomization kind of fails. You have to play further tricks, but that's for a different time. I've written a long paper about exactly that and what happens. There's much more known, but this is not a lecture on quicksort. I want to sketch how you can apply Chernoff bounds to prove this logarithmic height statement. But I have to identify something that behaves like a binomial distribution. And maybe that's at first not obvious how that fits together. That's supposed to be a t. Where's the binomial distribution? We have to make it so that it appears. So a little bit of notation. Let's say V is any node in this recursion tree. And n of V is the number of elements there. So in my picture, I would have said this guy is called V, and n of V is the length of its range here. That's n of V. And let's call J of V the random number of elements in the left subtree, or left recursive call. Okay, so in this case, the J would be this, the size of the left child. The thing is, I want to focus on a single vertex for a single node for now. So I'm describing these quantities from the perspective of one vertex. Of course, J of V is always this n of V of the left child. That's clear, but I'm trying to make make the point here. And now we say V is balanced if J of V divided N of V is in a good range, say between 3/4 and 1/4. So graphically, you want your pivot to fall in the middle range. And if it's too far, if it's in the outer half, the leftmost or the rightmost quarter, then you decide that that subtree somehow went wrong. Okay. But the point is, we don't care about individual failures. We just care about constantly failing. The key observation is if you have a recursion tree for n elements in the beginning, and you look at any path, then you cannot have arbitrarily many failure nodes which are unbalanced. So you cannot have arbitrarily many balanced nodes on this path. Namely, okay, the number you basically work out backwards and insert. But the idea is if you have a balanced node, you lose at least 1/4 of the elements, and you continue with 3/4. So the question is, how often do you have to multiply n by 3/4? So you start with n. The number of balanced nodes is how much this reduces. And you stop when you have a single vertex. So if you solve that for B, you get this, this quantity. Yeah, okay, I computed that this is 3 times 5 ln n. Probably won't need that because we don't do the full computation, I think. So you can only have so many balanced nodes before essentially the size of your tree reaches 1, and then you're at a leaf and you have to stop. The only way how your tree can grow arbitrarily tall is by having unbalanced nodes all the time. And so we're now almost there. We'll define our along any path. So we start at the root, and then we just follow an arbitrary path. And because the thing is symmetric, I'm going to just follow the left path, but the same statement applies in the end by a union bound over all paths. So the unquantitative statement is this. That's why we can focus on a single path. And we'll define indicator random variables that the ith node is balanced. And then you see that if you had a very long path, you would have many x's, but they sum to something much smaller than their expected value. So if we have x is the sum of many of these, say depth d, then that's, well, it's hopefully binomially distributed with some probability p, which will essentially be 1/2. That's how we picked it. We picked the balanced conditions so that it's equally likely to be balanced and unbalanced. And if that is true, then the probabilities say that the path is longer, whereas, sorry, that d is greater than, what's the constant that we should use in the end? Okay, let's leave it unspecified. A constant times log n for a large enough constant. That's the probability that our x is less or equal the magic bound. It cannot be more than this. But x is the sum of d random variables. So the expected value of x is 1/2 times d. And so you see, if you put c large enough, then the expected value of x is much larger than this 1.35 log n. And so you can apply Chernoff to this. I don't know, maybe we pick 7 ln n. So it's 14, so it's twice as big. Just to make up some numbers. So you can apply Chernoff bound to something like this. Now, I'm shortcutting a long computation for 2 reasons. Maybe it's insightful if you try it yourself to figure out what constants can make this work. But there's one little catch that I glossed over and that you have to fix. Namely, these xi are not actually Bernoulli 1/2 random variables, and they're not actually independent. They're close to it, and you can fix it, but not exactly as I defined it. And the reason is intuitively easy to see in the picture. And it all comes just from stupid rounding issues. If you have a certain size n and you're trying to split this, you don't have exactly probability 1/2 that you fall between 1/4 and 3/4 with your pivot, because n may not be divisible by 4. And so the probability is not exactly 1/2. It's something close to that, but rounded to multiples of 1/n. It's got to be. But that also means the probability for this guy is not independent from the balancedness of the parent, because the way the parent chose its pivot influences my size. So there's a sneaky, tiny little dependence that sneaks in. Because the pivot ranks has to be a multiple of 1 over n. Or the relative pivot rank, I guess. Let's say it has to be integral. So it's not, in the picture, I pretended that we have a uniform random variable at each level, and the truth is it's not exactly that. But the thing is, you can fix this by modifying your xi to be the combination of two events, that the pivot is in the middle, or if you know, because your size is not divisible by 4, that this won't exactly work, you add another option, you flip a coin with a small probability that offsets things so that, again, the combined event has exactly probability 1/2 to succeed, no matter what n of v is. I'm going to leave it here with this, because I think the details there are very quicksort specific and maybe not so exciting or general. But I found it cool that you can use the standard Chernoff bound by just applying some elementary clever tricks outside of it and use it for things where the exact assumptions are violated. As one concrete example, you can show that quicksort's height of the tree is greater or equal 42 log n out of all numbers, with a probability of order n to the minus 7.4. That's just what comes out of these numbers. There's actually even stronger statements about quicksort known. But standard Chernoff bound is enough to show our with high probability in big O. And remember, that means the constant in front of the log n can depend on the exponent for the probability that you want. Okay, so that's all for this introductory part with all these models and formal definitions. We've seen already far back at the beginning of the unit that there's examples where randomization is strictly more powerful than anything deterministic. That was this example of selecting the median. We've seen a formal model for specifying exactly what randomized computation is, which is mostly useful if you think about complexity classes. So we'll come back to that. We won't have to talk about the Bernoulli probability space much, but it's there for you in case you want to have things formally defined. More importantly, we've looked at two types of randomized algorithms: Las Vegas, where we can never answer a wrong output, and Monte Carlo, where this is fine as long as it's most of the time the correct answer. And we've seen Chernoff bounds as the key tool to prove that independent repetitions are really very, very likely to give something close to the expected value of some random process. I guess with that, we've set the stage. And so we could now go to actual randomized algorithms. As I said, for this unit, I decided to flip the order and first go to the negative results and complexity classes. And you'll see there's a reason for that, but I don't want to spoil the narrative just yet. Oh, we should also do a break. Probably should have asked other questions for the previous part. Applications of Chernoff bounds or any of the stuff before. Or not yet. So for the next part, the slides have changed a good bit. I wanted to add some new stuff about pseudo-random generators. And so that was a bit of a last-minute enterprise. So some more things to come, and I'll see whether we can do the full details is a bit questionable. Might take too much time. Somewhat off topic, but because a friend of mine sent me this. Did you know Python doesn't have binary search trees? It's kind of halfway proud not to, for some reason. It has dictionaries, but they're all hashing based. Now there's extra libraries that add sorted dictionaries, and there's in particular the sorted containers one. But they don't build a binary search tree or any tree structure. They essentially have a list of lists, and that's all. So you could say it's a B tree with height 2. But each of the parts is just a doubling array. And they claim that this is faster than any other option. And it kind of is, especially if you only read, because it's so fast. But then if you look at what happens with addition, if you insert things, you do scale badly if things become more expensive. But oh no, that's the normal list. They claim they're still faster than any tree data structures. That's incredible. This is Python because the performance there is a bit weird, right? The list part only uses fast things in C, whereas the trees need to allocate memory and so on. That's I'm not sure if the comparison is 100% fair. You could apply some tricks to trees, and I'm not sure they tried those. They seem to have taken existing implementations of trees and whatever quality they have. Okay, this has zero to do with this module. I don't know how to segue into this new unit now. Let's just start there. In the next unit, we'll look at complexity classes for randomized algorithms. For the other sections or the other big parts in the module, I swapped the order and first talked about algorithmic techniques, and then at the end, as kind of more of an afterthought, what are techniques to show that you can probably not apply what I've just shown you. Here, I don't want to flip it around and first talk a bit about what is possible or maybe not possible with randomization. I'm hoping to show some relatively advanced complexity theory bits in here, which at some point I might only sketch some details because it leads us too far. But there's beautiful intuitions to be taken from them. So I think it's worth the journey. And also there's some strong but unproven hypotheses with practical implications, I think. Let's start from the basics. The question that we ask here is how powerful is randomness? And we've seen examples like the median selection where it's provably improving, but it's not so clear how general this is and by how much it improves. The bigger theme in the unit in this module is P versus NP, polynomial versus, well, say exponential. Can randomness play in this league of differences? And in particular, from a complexity theory perspective, the question is, can you solve more decision problems or more problems in general with randomization in polynomial time than without? And so certainly we'll essentially look only at decision problems here and try to build up a bit of a cleaner complexity view on these things. And the first step towards that is to define some complexity classes for the types of algorithms we've already seen with polynomial running time. This not that much surprising to be there, but let's do it properly. First of all, we talk about decision problems only, which equivalently are just languages, subsets of sigma star, if we decide that's our universal input alphabet. And then, because we're talking just about accepting words or rejecting words from this language, the only three outputs that we'll use is 0 for reject, 1 for accept, and the question mark still is there as one option of saying my computation failed. I can't tell you whether it's in the language or not. I think we'll for most of it, not restrict how many random bits algorithms take. So they should be assumed to take a random bit in every computational step. At least that's the worst case that's possible. And with that, we can define several potential classes of problems. The first one is called ZPP, the zero error probabilistic polytime algorithms or languages. It's a set of all languages for which there is a Las Vegas algorithm. Okay, polytime is of course important, but that's going to be part of all these definitions. So just again to remind you, that's the weaker form, but we assume this always terminating variant. So there's some polynomial upper bound for the running time, and the success probability is at least 1/2. And also, if the algorithm outputs not the right answer, then it must output a question mark. Okay, so it cannot say a wrong thing. Las Vegas. That's ZPP. Then similar name but different beast is BPP, the bounded error probabilistic polytime problems. It's the set of all languages where we have a Monte Carlo algorithm, but crucially of the bounded error type. I keep stressing this, but you've seen it when we talked about Chernoff bounds now, that these are really different. So again, just to have that on the slide again, polynomial time, always terminating. And there has to be an epsilon specific to the algorithm, independent of the inputs, so that the probability for every input, there's a for all x in sigma star here. For all inputs, you output the right answer with probability at least 1/2 plus epsilon. It's the same as before, I'm just repeating the definition. We have a third type of algorithm, namely the unbounded error Monte Carlo algorithms. So to make things complete, let's also define a class for those. That's called PP, just probabilistic polytime. I don't know if people historically first looked at those. It sounds maybe like the most natural class. You just say it's any algorithm that has a polynomial running time, and it should be correct in strictly more than 1/2 of the cases. Maybe that's the most natural if you don't think about it, but you'll see this. This is not a good class. Those are the three main classes we'll look at. Now we can make a few assumptions to make life a little more convenient. We only bound the running time in terms of polynomial, no matter how big the polynomial is. So repeating an algorithm a few times is fine. In particular for the bounded error algorithms, we already know just some logarithmic number of rounds will actually boost you to with high probability. But what we'll assume is that we have a success probability of 2/3 if nothing else is stated. That will make one or two calculations easier later. That's true for BPP and ZPP. We know for PP, for the unbounded error algorithms, we can't actually make such an assumption and stay in polynomial time. At least not with a simple repetition. That's what we showed in the last section. But here comes the real bummer for PP. PP contains all problems in NP. And because while we're at it, it also contains all problems in co-NP. So this seems really strange, and it's just an indication that unbounded error is useless. You can do almost anything with that, which on the flip side means just because you have a unbounded error algorithm doesn't help you at all. But let's nevertheless prove this, because I think this is a still somewhat surprising statement, right? We're supposed to be able to do anything that a non-deterministic algorithm does with a Monte Carlo algorithm. And if you think about it, we always said non-deterministic means there's potentially just a single computation that accepts and all the others reject. That's far away from accepting with more than 1/2 of the computations. How's that gonna be possible, right? Seems hard to prove. The trick is that we can use the theory of what we know about NP to help us here. First of all, the class PP certainly allows any kind of polynomial pre-processing, right? Because that's so if I'm if that somehow helps me, I can take my problem and apply a polynomial time algorithm first to that problem and then solve what comes out. And that's going to stay in PP if the overall thing has a PP solution. That's a lot of P's. Because we're just adding a polynomial time. So in particular, we can apply polynomial time reductions to our problem. So in particular, we can say that L must polynomial time reduce to the satisfiability problem because that old friend was NP complete. So it suffices to solve SAT with PP, then I've solved all of NP, right? It's the same old story. And the way we'll do this will actually be general enough that you can do the same with co-NP hard problems. We haven't spoken a lot about co-NP, but it's kind of the flip side. So the general, the counterpart to satisfiability would be the tautology problem. Given a Boolean formula, decide whether it's a tautology that's true for any variable assignment. And we can use that to show the other inclusion. But we'll focus on SAT here. So let's try to do this. We have to give an algorithm, unbounded error Monte Carlo algorithm for SAT. Yeah, polynomial time, of course. So how do we do this? Given a formula. Let's say it has length n and k variables. Or we'll design an algorithm A. Give it a name. First step is you're going to do something random, right? So let's do something random. You just generate a random assignment. I guess uniformly. I'm just going to call it V from the variables to 0, 1. And this doesn't need much explanation. You just pick k random bits for that. And then you check if V makes A true, phi true, then we output a 1 because we've obviously proven that the formula is satisfiable. And otherwise, That's the tricky bit, right? What are we going to do now? Otherwise, we flip a biased coin and output whatever that coin says. And the trick is to choose this probability right. And it's essentially 1/2, just a tiny tad less. K plus 1. Let's make this a bit less absurd. So I'm going to take a coin that's ever so slightly bent towards coming up as 0. So it's strictly less than 1/2, but ever just so slightly. And the claim is, number one, what's the running time of this? Let's do that first. This is linear in K. This is linear in N, I guess, or at least polynomial in N. And this is maybe even constant expected, at least. We've seen the discussion of how to generate things like that. But let's be generous and maybe say K, because you're probably going to need K bits to do that simulation. Doesn't matter much. Certainly polynomial. It's actually even linear, but so that's fine. How about the correctness? We have to show that we output the right answer. The probability that A outputs phi needs to be the same as A is satisfiable. This is a claim. Strictly greater than 1/2. That's what we claim. And so we'll do a case distinction. If phi is in SAT, then we'll always output that, right? No, sorry, forget it. It's not true. But if phi is satisfiable, at least one satisfying assignment exists. For the variables x1 up to xk. Now, in the worst case, there's a single one. That's the only thing we can say. But still, the probability that step 2 succeeds is at least 1/2 to the k. Because there's 2 to the k in assignments in total, and at least one has to be satisfying. Okay? So then let's analyze what's the overall failure probability that A outputs 0, which is wrong in this case. So for the output 0, we must fail in step 2, right? We have a nice. Let me write for this B of phi equals 1, okay? Because it's annoying not to have a notation. It's just we need some notation for a formula under a variable assignment. What's the value of that thing? I don't want to write these variable substitution in square brackets all the time. So it's the probability that our random assignment that we pick says this thing is false. But if that's the case, then we continue with step 3, which is flipping this random coin. And we do this with fresh random bits, so it's independent of the previous thing. So that has also to be 0. I guess here we use independence. But that's harmless because we're generating these, we're making them independent by running step 2 and 3 with with disjoint random bits. Okay, then we just have to calculate, and I'm running out of time. So this was the counter probability for this. So can't be less than this. And this one was by choice our counter probability for the other thing. And now we just find that this is less than 1/2, right? I do the math and multiply it out. So if the formula is satisfiable, we reject it with a probability less than 1/2. And the second case, luckily, is easy. If the formula is satisfiable, then the probability that our random assignment satisfies it is 0. And so the overall probability that this one is wrong, that it accepts, is going to be 1 for namely the output that we have to do step 3, and then again our p, the probability that this is 1 this time, and that's p, which is less than 1/2. So again, the probability that we output the wrong result is less than 1/2 in both cases, which means the overall claim is shown, namely the probability that we output the right thing is more than 1/2. And that was what we wanted to show. So that if you had any doubts before this proof, this certainly drives home that PP is not interesting. You need bounded error Monte Carlo algorithms for any kind of interesting results, both practical and for the error probability, and in theory for having interesting complexity classes. Goodie. That's that, and we'll continue next time with 2 more complexity classes before things get fun.